Tractography. In neuroscience, tractography is a 3D modeling technique used to visually represent neural tracks using data collected by diffusion-weighted images, DWI. It uses special techniques of magnetic resonance imaging, MRI, and computer-based image analysis. The results are presented in 2- and 3-dimensional images. In addition to the long tracks that connect the brain to the rest of the body, there are complicated neural networks formed by short connections among different cortical and subcortical regions. The existence of these bundles has been revealed by histochemistry and biological techniques on post-mortem specimens. Brain tracks are not identifiable by direct exam, CT, or MRI scans. This difficulty explains the paucity of their description in neuroanatomy atlases and the poor understanding of their functions. MRI technique. Tractography is performed using data from diffusion tensor imaging. The free water diffusion is termed isotropic diffusion. If the water diffuses in a medium with barriers, the diffusion will be uneven, which is termed anisotropic diffusion. In such a case, the relative mobility of the molecules from the origin has a shape different from a sphere. This shape is often modeled as an ellipsoid, and the technique is then called diffusion tensor imaging. Barriers can be many things: cell membranes, axons, myelin, etc., but in white matter the principal barrier is the myelin sheath of axons. Bundles of axons provide a barrier to perpendicular diffusion and a path for parallel diffusion along the orientation of the fibers. Anisotropic diffusion is expected to be increased in areas of high mature axonal order. Conditions where the myelin or the structure of the axon are disrupted, such as trauma, tumors, and inflammation, reduce anisotropy, as the barriers are affected by destruction or disorganization. Anisotropy is measured in several ways. One way is by a ratio called fractional anisotropy, Fa. An anisotropy of 0 corresponds to a perfect sphere, whereas 1 is an ideal linear diffusion. Well-defined tracks have Fa larger than 0.20. Few regions have Fa larger than 0.90. The number gives information of how aspherical the diffusion is but says nothing of the direction. Each anisotropy is linked to an orientation of the predominant axis, predominant direction of the diffusion. Post-processing programs are able to extract this directional information. This additional information is difficult to represent on 2D grayscaled images. To overcome this problem, a color code is introduced. Basic colors can tell the observer how the fibers are oriented in a 3D coordinate system. This is termed an anisotropic map. The software could encode the colors in this way. Red indicates directions in the x-axis, right to left or left to right. Green indicates directions in the y-axis, posterior to anterior or from anterior to posterior. Blue indicates directions in the z-axis, foot to head direction or vice versa. Notice that the technique is unable to discriminate the positive or negative direction in the same axis.
Please subscribe and thanks for watching.